I'm here to discuss about parallel RLC circuit. So in this circuit analysis, we're talking about current in each branch, total current in the circuit, vector diagram, the power, the magnetizing bars, and power factor and impedance. So in this circuit analysis, its configuration is a resistor that is parallel to a sinusoidal source, a parallel capacitor, and a parallel inductor. So let's put R here to represent the resistor, which will be measured by ohms. Then we have our capacitor here, which will be represented by C, and it is measured by farad. And there is an opposition of current that is associated in this capacitor, which will be labeled as our X sub C. And as our previous discussion, this is the capacitive reactance, and we can solve this by using the formula of X sub C is equals to 1 over 2 pi times the frequency times the value of the capacitor in farad. So in our inductor, will be labeled as letter L, then it is measured in the unit of henries. So there is an opposition here also, which we call the inductive capacitance, which will be labeled to X sub L. And from our previous discussion also, that this is the inductive reactance that can be solved using the formula 2 times pi times the frequency times the value of the inductor in henries. So we will just call here this as our source, and we will be label this as E sub O. Then we will assign values to solve the current and everything else in the circuit. So our E sub O is equal to 15 volts, and we have a frequency of 60 hertz, and our resistor is 50 ohms, and our capacitive reactance is let's just say 25 ohms, and our inductive reactance is 70 ohms. Now, the unit of capacitive reactance is ohms and inductive reactance because it is the opposition of current in the capacitor. It means that it is also a resistance. That's why we're using ohms. Then I'm giving the value of capacitive reactance in an inductive reactance because we will be using Ohm's law to solve the current in each branches. So if you were given the value of a capacitor, you can use the formula to derive the capacitive reactance and inductive reactance so that you can solve the branch current. So now we're solving the branch current. So by Ohm's law, I is equals to V over R. We all know that the voltage here and voltage drop across here and here and here are equals because this is a parallel circuit. So we will have 15 volts all over the resistance, which is 50 ohms. This will be 0.3 amperes. Now, here in the capacitor, we can solve the current. I sub C is equal to the voltage drop here, V sub C all over the capacitive reactance, because we need resistance to solve the current. So over X sub C should be 15 volts all over 25 ohms. And equal to 0.6 amperes. Now, here in the inductive area, so I sub L is equals to V sub L all over the inductive reactance, which is I sub L 15 over 70 0.214. Now we have the branch current. So now we have 0.3 amperes here, 0.6 amperes here, and 0.214 amperes here. Now we will solve the total current. So the current here is the I total. Now we cannot use in AC circuit we cannot use algebraic process to solve the total current, because unlike in DC, which all elements are in phase, you can use algebraic process. You can just add the current here, the current here, and the current here. But in AC system, you cannot use algebraic process. You can use vectorial process. So now we will form the vector current vector diagram. So the current in the resistor is our reference vector. So it will always going to the right. So this is our current in our resistor. 0.3 amps. So now, the current in the capacitor is going downward because of its formula. That is an inverse, and the answer is always a negative imaginary number, so it will going down. So we have 0.6 here, a vector pointing down. 0.6 amperes. And the current in our inductor is 0.214, is pointing up because it is 180 out phase of the capacitor, and it is 90 degrees with respect to the line source. So that'll be IL, which will be 0.214 amperes. Now, as you can see, the vector pointing down is much bigger than the vector pointing up, so we can just subtract it and shorten the vector here. So you can just erase the vector from the current of the inductor and subtract it from here. So we have 0.6 minus 214. Which will be 0.386. So just erase this. .386 amperes. Now we will extend. We will put we're forming the right angle here, so we can put the hypotenuse here. So this hypotenuse represents the total current. So put IT. Now we can solve the total current by using Pythagorean theorem. So IT equals to the square root of R squared plus here this IC minus IL squared. So this is the formula in solving the total current. Now we will solve the total current. So it's a substitute IT that I mean IR. So IR is 0.3 amperes squared plus value of our IC, which is 0.6, minus the value of our inductor, 0.214 squared. Should be equal to 0.489 amperes. So this is our total line current. So at first glance, you would say that this is wrong because you will, as you look at the value of the current in the capacitor, this is 0.6 and the total current is 0.489. So you can say that it is wrong, but actually it is right. Because here's the thing. So there is an exchange of energy here in the capacitor and inductor that is not reflected back in here. That's why we have bigger value of current in the capacitor, and in reality and in physics, the collapsing and expanding, the magnetic field of capacitor is the collapsing and expanding magnetic field of the inductor is supplying current to the charging and discharging electric field of the capacitor. So that's why we got bigger current here than our line current. So now we're talking about magnetizing bars. So these are the given from our previous circuit, and these are the answers that we calculated using Ohm's law and other laws. Then now the magnetizing bars required from the inductor can be solved through these three formulas. So one is bars equals voltage times the current in the inductor. So 15 times 0.214 amperes equals 3.21 bars. Or this formula, bars equals the current in the inductor squared times the inductive reactance. So 0.214 squared times 70 is 3.21. Or bars equals B squared over the inductive reactance, which is 15 squared over 70, 3.21. Now let's go to the capacitor, the magnetizing bars of the capacitor. So the formulas is just the same with the inductor, but they just replace it with, instead of the current in the inductor, they use current in the capacitor. Then they use the capacitive reactance, and we got 9 bars. So let's go to the net bars. Then the net bars is the difference between the magnetizing bars of the capacitor and the inductor. So net bars equals 9 minus 3.2, and we got 5.8 bars. So now we're talking about the power of the circuit. So the power of the resistive branch is the overall power of the circuit, because the capacitor and the inductor is 90 degrees outphased with respect to the line source. So as a result, they have taken zero power. So the power of the resistive branch is the whole power of the circuit. So these are the formula to solve the power of the circuit. So P equals V times the current in the resistor. So 15 times 0.3 equals 4.5 watts. Or P equals the current in the resistor squared times the resistance. So we got 0.3 squared times 50 equals to 4.5 watts. And another is P equals V squared over R. So we have 15 squared over 50 equals 4.5 watts. So here we will solve the total impedance of the circuit. So we have formulas here to solve the total impedance. So Z, or impedance, equals voltage over the total current. So 15 over 0.489 is equal to 30.67 ohms. And another formula is Z equals 1 all over the square root of 1 over the resistance squared plus the parenthesis of 1 over the inductive reactance minus the capacitive reactance squared. So we will just substitute the value, then we got same answer as here, or maybe differ some points, but actually it's the same. So 30.697 ohms. Now we have another formula here, but in this formula we need to the value of the inductive reactance is positive and the value of the capacitive reactance is negative to determine whether the circuit is more inductive or positive or more capacitive negative. Then we have to solve the value of X first, where X equals the inductive reactance times capacitive reactance all over inductive reactance plus capacitive reactance. So we just substitute the value here, 70 times the negative inductive reactance, negative capacitive reactance all over 70 plus negative 25 is equal to negative 38.89 ohms. So now we have the value of X, so we will just substitute it from here, from this formula. So 50 times negative 38.89 all over the square root of 50 squared plus negative 38.89 squared, we got negative 30.698. So we can say that our circuit is more capacitive.